This is Hamid Khan here from Sydney. My background, तो मुझे आपको मैंने बता दिया है पहले. It's a civil engineer, been almost 24 years in the industry. Delivered almost more than 500 CPD workshops, training programs, right in the Gulf, Middle East, Dubai, Bahrain, Oman, Kuwait, Qatar, Abu Dhabi, Saudi Arabia. And obviously a few in Toronto, in US, New Orleans, in Australia, and in New Zealand and South Korea. So I was thinking that I'll make some slides of my presentations in different parts of the world just to share maybe some other time. So today's topic is concrete durability and risks in concrete structures. It's a very wide topic, so probably it will take, if not, months and weeks, then days it need, to cover such a vast topic. So in this short 45 minutes, I'll just try to cover as much as I can, and then we'll definitely have a Q&A session, and afterwards I'll definitely share my email and my contact details for any future discussions. So the first picture on this slide is a very interesting picture. This is one of my favorite pictures and images. And it tells a lot of story. If you see the right-hand side, it's the honeycombing in concrete and a defect in your new concrete structure. And an image on the left side, it shows a distressed concrete where the depassivation has started and corrosion has started. The rusting of steel has started due to chloride attack or carbonation or whatever. And this could happen in any of your structures, in your towers, in your columns, beams, your bridges, tunnels, any of the concrete structures. So this is a picture that I had while I was in Toronto just before the COVID started. I think last year is somewhere in October. And we were working and applying some galvanic cathodic protection for these a massive bridge. In Canada, you have a lot of de-icing problems that we don't have it here much, but that was an old structure. But definitely, in addition to aging, we also have premature deterioration is another challenge. Premature or accelerated deterioration. I'm not sure if you've heard about David Chandler, who is the New South Wales Commissioner for Building. He has been very active recently in getting the things streamlined after having these issues in Opal Tower and Mascot Towers in Sydney and some other structures, mainly in the building sector. We can say that the building side and in the infrastructure side has been pretty streamlined because the asset owners over there, the road authorities have really worked very hard in providing a good durability parameters to meet those parameters. So definitely I'm not going to talk about, this is not an error slide, but this is just to make a point here that a lot of infrastructure projects are coming in, but my presentation is not limited to infrastructure, but also for buildings and some other structures. So American Concrete Institute ACI conference award-winning paper in 2013 was how to develop better project specifications. My point here is that when we say project specifications, it doesn't mean only for new structures, but also for structures which require rehabilitations, refurbishments, and massive repairs, such as bridges or any other structures. So contents, introduction, durability concept. We'll talk about a bit on service life and deterioration of concrete and risk factors, innovations in concrete remediations, some case studies. We'll try our best to conclude, with some thoughts. 2080, in 1950s, I think the concrete and the concrete gurus here can second me. The concrete used to be designed at 20 megapascal at one time, probably in 1940s, 1950s. And it has been evolved after years and years and decades. And today we can see the concrete is being designed also for 80 MPa. And even sometimes I've seen 100 MPa as well for some of the towers. So concrete is is very simple. It's so simple that probably, what is it? Heterogeneous. I cannot read this even. So forget about it, guys. Forget about it. Concrete is very simple. It's sand, aggregates, cement, water, and admixtures and additives that we add in order to make your concrete workable and to use it. I was involved in Burj Khalifa, the tallest tower of the world, concrete supply for the piling. The piling for Burj Khalifa was almost 2-meter dia piles. So our company supplied at that time, which was Fosroc, the self-compacting concrete additives for the 2-meter dia piles. All the piling were done by self-compacting concrete. Now, also the superstructure was done by self-compacting concrete supplied by another company. What I'm trying to say, the standards were very high for that structure because the design life and the service life of that structure was exceeding maybe 100 years. I don't remember exactly. And I think Australian consultant, one of the Australian consultants was involved in the structural assessment of that structure as well. So we all know about these, concrete is good in compression and what is tension, weak in tension and flexural stresses, and that's why we have steel reinforcement, something very basic that I just thought to run quickly on that front. We all know that concrete has an inherent property to provide protection to steel reinforcement because of the alkalinity of the cement and the concrete. So there is a natural occurring protection film on your rebar steel reinforcement for the protection because of the concrete matrix, because of the alkalinity of the concrete matrix. And that provides a highly alkaline environment. If anything is between 1 to 6, you know that about the pH, it's more towards the acidic. 7 is neutral. The more we go from 7 to 14 is alkaline. And concrete basically protects the steel due to its alkalinity. So we all know that concrete, corrosion of steel in concrete, and being working 17 years in the Middle East and the Gulf, I can say that Middle East is one of the most corrosive environments for the reinforced concrete structures. Well, I've seen even in Sydney and coastal areas in Gold Coast, Queensland, there are some massive corrosion problems in the buildings. Even the structures that are located, and we'll talk about it in a while, close to the marine environment, they are susceptible to more corrosion because of high humidity levels and temperatures. So our structures are subjected to various external environmental factors. You have rain, you have airborne salts, you have wind, sun, salt spray, and the moment you will have cracks in your concrete or problems in your concrete, your steel within the concrete is challenged. So the whole point is, what I'm trying to make a point here, that none of the defect in concrete is cosmetic. Even your pinholes, your blowholes, cracks, shrinkage cracks, whatever is showing upon your new concrete, it needs to be treated. Here is another good example. You can see poor concrete is being subjected to, if you see the right side, soil, you have sulfates in soil. Atmosphere, you have carbon dioxide, atmospheric carbon dioxide, you have airborne salts and chloride that will attack your concrete. Mechanical, you have wear and tear of your concrete. In workshops, in other car parks, and bridge structures probably. And the left side, you can see the red part is the most dangerous, the most critical attack on the concrete is coming from the tidal and splash zones, where you have cyclic wetting and drying of your that particular structural element. And that would lead to very brisk corrosion rates because of that cyclic wetting and drying. That's why even in submerged, because of lack of oxygen, you don't have that brisk rates of corrosion. But when you see in marine environment, you have a pier, and we are doing a lot of bridge repairs and with galvanic anodes for RMS and other road authorities as well, Transport for New South Wales, and for other road authorities as well involved, and councils where they have aging bridge structures and the piers needs to be protected. And the areas where the piers are subjected to wetting and drying cycles, that is the most critical segment that needs protection against chloride and carbon dioxide. So that means when I say that we need to protect our steel from what? Carbonation, chlorides and sulfates, and obviously there are so many other factors, but these are the main ones, and we call it corrosive agents. Now, durability. Durability has become a buzzword. Durability debate, durability of concrete, durability design, durability concept. So there are two ways of defining durability, dear fellows engineers, the non-factual way and the factual way. And that's very interesting. When a structure is considered durable, when it performs satisfactorily and maintains acceptable appearance, you know, some people, they call it it's durable. That's a very subjective way and non-factual way. The moment you define durability in terms of its service life, that these, for example, the structure would perform satisfactorily and acceptable appearance for a certain number of years, that means you have combined the non-factual with the factual in terms of number of years, in terms of service life. So the moment you will have a service life requirement, your non-factual thing would become factual, and it makes more sense. So the true definition of durability would be then the number of years during which the structure shall perform satisfactorily without unforeseen high cost for maintenance. Now, this is a very famous 2T model, a very old one, but a very reliable one, 1982. It says that in the initial phase, and then you have a propagation phase. And then you say, what is the service life, the technical service life? It extends a bit more towards propagation. But it doesn't say that your service life is up till the end of propagation phase. End of propagation means where you have concrete pieces starts falling down and you have a stage 4 disaster of concrete. It's a concept. It says that, okay, theoretically, technical service life ends here. I personally believe there are better models now coming after this. This is a very old way of thinking, because these days we have a lot of interventions and maintenance cycles that we go through it. For example, here is another way of defining a service life. At number 1, you have depassivation. When the concrete is challenged, you have cracks. Number 3 is spalling. Number 4 is collapse. So you have initiation and propagation. This is the best model that I like. That says that your service life, it extends right from initiation till the end of propagation stage, till the failure. In the initiation stage, you have shrinkage cracking. With the time, if you see on the right side scale, you have carbon dioxide, atmospheric carbon dioxide and chloride attack. You have corrosion and steel and stress generation, because after corrosion, what happens? The steel expands 6 to 10 times of its volume, and they are expensive stresses, and your concrete is spalled. So then you have failure of the structure. But the point is that interventions. So these days, all the road authorities, all the asset owners, they have a planned maintenance. There, you know, there is one durability risk that has been identified by many scholars and researchers, that maintenance negligence. Maintenance negligence means that you wait till the end of the propagation stage, till the structure has to a stage that has reached to a stage where it can't really be repaired. So service life could be, some people define it as warranties. Then you have design service life. Then you have real service life. Can I ask everyone to mute your, to put yourself on mute? Thank you. So normally most of the products and structures, they last far beyond their design service life. And that's what some scholars, they call it rear service life, but we'll talk about it as we go. It's getting more complex. suppliers being asked that, can you provide your design life statement for your products? Because the structure that has a defect could be a bridge that has been designed for 100 years. Now they want a written statement from suppliers that, can you provide some repair mortar, for example, that could also last for 100 years, and that makes sense. But that's not applicable always. So there are a lot of debate about these type of things. And if you happen to come across to similar type of requirements from asset owner, please do contact me and we'll find a way. So buildings have a design life. This is 2003 research paper that says 50 to 60 years in New Zealand, Australia, 50 to 60 years. It's been quite old. Maybe things have changed now. In Japan, 20 years, really? USA, 35 years. This is one of the papers. This is not me, Hamid Khan, saying, but this is a source from Shaba 2003, Williams 2002, and Douglas 2002 papers. Okay, now this is a very interesting slide. It talks about bridge hierarchy. You know, one bridge has different segments and elements and sub-segments and elements. Deck has wearing surface, deck top, soffits, drainage systems. Similarly, you have beams and longitudinal elements, girders and floor beams. You know that they have been also being formed in precast yards sometimes, and some are cast in situ. I'm not sure if they are really cast in situ these days. Abutments, abutment walls, wing walls, bearings, piers, columns, caps, bearings. These are all, each and every segment and element and subsegment is subjected to atmospheric attack. That's why the moment you have these problems and honeycombing, what happens? The asset owner immediately asks you to provide this durability statements and design life, because they know that their structure has been designed for 120 years, 100 years, and it has not come into service yet for a single day, and there are some massive defects. So that, what does that mean? Do we have to knock it down? No. These days, technological advancements and innovations have reached to a level where you can reinstate the structure to its original structural integrity and strength. So why does concrete deteriorate? There are a number of factors. I don't want to name those. We'll spend a whole night over here about, but there are a number of factors that are that could be responsible. It could be poor design, poor workmanship, poor compaction, abrasion, fire, leakages, environmental factors like carbon dioxide and chloride attack and settlement, seismic earthquakes, chemical attack, mechanical damage, something has bumped into the column in the car park. Poor workmanship is something which is
interrupting you.
Yeah.
हमारा सेशन शायद नेक्स्ट 1 या 2 मिनट से डिसकंटिन्यू हो जाए, तो अगर ये डिसकंटिन्यू हो गया तो आप सेम लिंक को ज्वाइन करेंगे तो you will be back in.
Correct. Okay.
Thank you.
So durability menu of possible materials. This is a durability menu slide. This is, I've taken it from Mr. Faiz Khan. I was working with him in Dubai, and I really like this slide. So I've referenced this gentleman as well. It's very interesting. And that says that how okay, so I think I was muted as well. Okay, so can you hear me?
Yep, we can hear you.
So durability menu means these days concrete is being designed by number of single blend, double blend, triple blend, fly ash, GGBS, supplementary cementitious materials, a lot of other admixtures, additives, self-compacting concrete, corrosion inhibitors and all that. But despite of all that, we are having such a great concrete. We have these type of problems. And none of my images are from Google or website. They are all real pictures from different parts of the world. This is new defects, can you believe? So what happens is that obviously this is a picture in 2002 in Shangri-La Hotel in Dubai, where the first time I've experienced using self-compacting concrete. Because when your steel is congested to a level, they were like transfer girder beams, and it was at a height of, I don't even remember. And this is me when I was young, probably, I don't know, 26 years ago, 20 years ago. And you can see the steel at the bottom, so congested. If you are using your conventional concrete, you're going to end up having big honeycombing. So that is the point here, that we need to select the right products in order to have the right solution. This is a problem and a big honeycomb void, a project in Australia. I don't want to name it, but this is a defect in the new construction. What does it mean? The engineer might say, knock it down. But these days, aging factor is one, where we are having an concrete deterioration because for the old structures and existing structures, we can't deny it. But the problems and the concrete defects in new structures is always very important. So the engineers who are working with asset owners, or with asset owners who have working in very important structures of high design life, and if you're having some massive cracks or any type of deformation or any defects which are not highly structural but could cause and lead to structural failures, they must be addressed without a masala mortar, but with a proper rectification and design strategy. Shall we continue, sir?
Yeah, I think we should start now.
Yeah. So these are all. This is from Australia here. This is from Australia as well. This is also from Sydney. This is also from Sydney. And column is the I think these are two projects that I've mentioned here. So column is your structure is basically, it's a load-bearing structural element. You can't really play with it. So if there are problems with column due to slip of formwork or due to any problem, it has to be rectified using proper repair mortar. These days there are repair mortars which are available as self-compacting concrete, similar to those that have been used in Burj Khalifa, but they are available in pre-bag. That means you don't have to bring your transit mixer with 9 cubic meter or whatever the cubic meter for such repairs. You can use pre-bag micro concrete pourable materials to repair such voids in structural elements by creating, we call it foam and pour. So you create a letterbox formwork and you pour your material and it would just reinstate it 100%. This is a slide from Transport for New South Wales, or RMS B80 specifications, that tells us about, for their durability specifications, they have different exposure classifications. They have different requirements for chloride diffusion resistance, which is 3.5 for B2. It's not applicable for exposure classification A and B1, but for B2, C, and CU. What is C? C is marine environment. So anyone who's working in marine, this is C. So they have a very stringent 2 multiplied by 10 raised to power by minus 12 square meter per second. Can you see my cursor? Is it possible to see my cursor?
Yep.
Okay. So this is very stringent property, and I would say if you are using any repair mortar, this should meet this requirement. Otherwise, RMS or Transport for New South Wales, they are not going to approve it. Similarly, they tell us that their B80 specifications for concrete says a minimum of 65% of blast furnace slag and so on. So what I'm trying to say that in RMS specifications, and similarly it might be for other road authorities, there are durability parameters defined as per what should be the chloride diffusion resistance, carbonation resistance, what should be the supplementary cementitious materials. I just wanted to make a very important point. A lot of people that think about, when you're talking about supplementary cementitious materials, SCMs, a lot of people that think about it, hey, that's an environmental green, who cares, you know, it's not really important. It's not about only green and environmental friendly, but it's also very important because if you are replacing your cement with fly ash or GGBS, blast furnace slag, what are you trying to achieve? You are trying to reduce the cement, and cement, when you reduce cement, the chances of cracking and shrinkage is less, isn't it? So that's how the SCMs, these supplementary cementitious materials, become the part of durability package. So it's not about environment only. Reduction of cement is good because you reduce the carbon footprint, etc., etc., etc. But it basically improves the durability of your structure. And that's why Transport for New South Wales have mentioned a certain percentage. It's a very high percentage that is being used in your concrete of 65%. When you're talking of Class C, when you're talking of Class B2, they say it's 50%. What is B2? B2 is permanently submerged and in spray zone, it's C1, and C2 is the splash zone, where you have, when you say splash zone, if you're piers, if you are in a marine environment, where you have continuous wetting and drying cyclic movements of water, that is C2, the most aggressive exposure classification for any concrete is Class C2. So that's why they have for Class C, the chloride diffusion resistance value as well. Below are the products that I deal in and I work in. And the purpose of this presentation is not commercial here, but I had to take these names of the products just to show you that how they meet all these exposure classifications and which one do not meet. So that means they can be used in the benign environment. Others you can easily use in high classification environment. So this is something serious because we need to protect our structures with the right products. These are some of my articles. I would suggest it's an excellent platform to share that with you. I've been keep on sharing that in LinkedIn and some other forums, but please do read them in your leisure time. The left one is water leaks in multi-story buildings and corrosion problems. It's a very good article. And the right side is concrete problems today are multifactorial and what are the root causes. I'll try to run this quick animation and see if it really works. If it doesn't work, Gilani, please let me know.
Yep, it's working.
Now, this is a very interesting quick animation. This is your retaining wall, steel arrangement, steel reinforcement. You have a formwork and you apply your formwork and then you pour your concrete, isn't it? A normal conventional concrete, you compact it. If you're using self-compacting concrete, you don't need compaction. You remove the formwork and you end up having big honeycombing. We are all human beings and we end up having these type of issues. So the steel is exposed, environmental factors, chloride attack, carbon dioxide will attack the steel, try to destroy and attack the passive layer of the steel, the passivity of the steel. Maybe we could have another session on corrosion. For all those who are interested into anodes and cathodes and corrosion, let me know and we can talk about it later on. But this is what happens at the end, that spalling effects and your concrete deterioration for a new structure. So a lot of problems. We have different kinds of problems that needs to be addressed. So we need innovation approach to address these problems. The philosophy of repair and rectification, it right away starts from structural information. It doesn't start from the product. Oh, yeah, what is the product can be used for this? No, that means you are neglecting and omitting these structural information, assessment process, management strategy, design of repair, and you're trying to reach directly to number 4, number 5. So we cannot cover that all today. So maybe I just run through very quickly. Structural information, if you are working for a project, any problem, you need to understand what is the history of the structure, how old is the structure, what products were used in the past in order to know any compatibility issues. Because there are a lot of compatibility issues when you are using different types of products. What is the general construction, where is it, what was the problem, previous drawings, all the history. Then you start an assessment process. I'm sure we have some engineer fellows here who are working into labs and condition assessment companies. I've seen some of the chats, you know, they are working. They do the assessment process. The reason of the failure, they do chloride sampling, dust sampling. Has the chloride exceeded the threshold value percentage by weight of concrete or cement? The normal test for carbonation can be done. Non-destructive testing, semi-destructive testing, destructive testing, all those core testing, these are all parts of the assessment process. There are different individual seminars for this assessment process. I don't want to go through that in detail, but this is very important to understand the root cause of the problem. If there is a dead cat in the water tank and you keep on changing water filters, it's not going to solve the gastro problems, isn't it? So the gastro problem can only be solved if you remove the dead cat from the water tank. So what I'm trying to say, in concrete repairs, there is no room for cosmetic repair. There is no room for a masala mortar. There is no permission to be superficial and just do a cosmetic touch and repair and masala mortar thing. It has to be addressed as per the root cause, and to understand what is the root cause of the problem. And this is more applicable for old structure and existing structure. For new structure, we know that it's new, it's honeycombing, it's a defect, workmanship or whatever, shrinkage cracks or drying shrinkage and these type of problems. This is $1 million picture because these are my hands. So I was passing through a car park in New Zealand. I had this bandage and I was just trying to make a point here that none of the cracks, none of the defects should be cosmetically repaired. It has to be, there is no aspirin fix. There is no bandage fix. It has to be assessed and repaired, rooted out and filled up with a proper product. Could be epoxy injection or could be a normal filling of material. Then you have number 3, management strategy, where you can assess the condition of the structure. Do you really want to go with it or demolish it or do nothing strategy, or what type of, you discuss different strategies where you also talk a lot about budgets and all that activities. As I said, I'm not going to talk about these in details. I'm coming back to step number 5, which is more important, step number 4. Step number 4 is the design of repair. When you start talking about the strategy of the repair, the techniques of the repair, that, hey, okay, it's let's use hand applied high bill mortars. Let's use foam and pour because this is very important, and you have big gaps of more than 50 millimeter. It goes up to 500 millimeter thick void. Do we need to demolish it or knock it down? No, you don't need to do that. There are products which are available. You have sprayed on repair materials for larger areas, for overhead, where you can spray. And you have special bridge repair materials for pavement repairs as well, and I'll show you some real examples of that. This is a very important slide. I've just added in my last few slides. I've given a presentation to PEiA Concrete Institute of Australia recently. In that webinar, I have just added these 2 slides. This is very important. The concrete repair mortars or the concrete has to be compatible with the host concrete. It has to be low permeable, and there should be long-term integrity. That means I've given that in detail, and you won't find it in any paper. These are my slides. When we say compatibility, that means your repair mortar should have the model of elasticity, the thermal coefficient of expansion, and the strengths, compressive strength and flexural strength. They should be compatible with the parent concrete, with the host concrete. So if you have a structure of 70 MPa, you don't repair it with 20 MPa or a 30 MPa. Or if you have a structure of 30 MPa, don't repair it with 70 MPa repair mortar. So that's important. Low permeability is important. Low permeability means against water, carbon dioxide, and chloride. Long-term integrity, the bond strength is very important, and the shrinkage, low shrinkage. The most important property of a repair mortar is having low shrinkage. So less than 300 microstrain or less than 500 or 600 microstrain at 28 days is something great, is something very good. So that is very important. These 3 properties are very important for repair mortar specifications. Sometimes we just see a compressive strength, 70 MPa repair mortar, let's go ahead and do it. And you're gonna have cracks because you haven't assessed the shrinkage property, the bond strength, and so on. So these things are very important to understand while selecting a repair mortar. You see, the more drying shrinkage you have, this is the left side is the drying shrinkage. It has increasing crack potential as you have more and more drying shrinkage. We can talk about drying shrinkage some other time. It's just the calculation is very simple. The change in length divided by the original length multiplied by 10⁻⁻⁶ will give you microstrain drying shrinkage. And as I said, this is one of the most important properties for a selection of a good repair motor while you are repairing these high design life structures. So most of the suppliers, they won't write it on their technical data sheets. This is a sample durability design for a good repair motor where it tells about bond strength. One thing is very important, I think I should mention here, and I've seen a lot of engineers, they struggle with this. For large refurbishment projects, if a product says that it has a bond strength of 3 MPa adhesion, pull-off, that doesn't mean that at site it should give that 3 MPa value. This 3 MPa is as per, for example, Australian standard or EN 1542 standard. At site, when you're doing it, Vic Roads and some other engineers, they say that 0.7 MPa is good enough. With none of the values should be less than 0.65 mean values. So when you are doing a site trial sampling and a pull-off test, it's a bit different than the laboratory controlled bond strength testing. So guys, then you have the repair work, you see how many steps we have discussed before getting into actual repair. And this is one of my articles. It tells about pre-prepared. Is surface preparation for concrete repairs a fad? No, it's not a fad. It's very important. And again, in your leisure time, please read this article. This has been published in many leading Australian magazines, and this is Australasian Corrosion Association magazine. It tells a lot, and it covers the surface preparation in totality. Like when we say, when you are renting a house or when you are purchasing a house, what are the 3 most important things? You say location, location, location. And I would say when you are preparing, when you are repairing a concrete, there are 3 most important things, which we call it surface preparation, surface preparation, surface preparation. I'm just trying to make a point that it is so important, even if you apply a gold and if your surface is not prepared properly, it's gonna fail, it's gonna debond. It will act as an alien body. It will not act as a monolithic part of your parent and host concrete. So if you really want to reinstate the structure, I was with one of the asset owner engineer, he's a doctor, and he was just trying to make a point. He said, even I don't want to call repair of our structures when it's a defect in new structures. I want to call it rectification. He was just trying to make a point that, hey, this is a structure that has been designed for 100 years, and it is just during construction there is a defect. So we don't want to repair it, we need to rectify it. We need to reinstate it to its original structural strength and durability. So this is how important it is that the asset owners are so sensitive about the new construction defects to be rectified properly, because they want the structures to last for the designed service life. So this is a separate session on how to repair and clean the steel and how to apply repair motors. Let me see if I can run this quick video, if it works. Is it working?
Yes, it's working.
A very typical example of, if you have an overhead repair, you saw cut the edges and then apply a special motor. It's not a masala motor. It has to be a specially designed motor that has a non-sagging property. And then you apply a curing compound over it. One thing that I've missed to mention here is that pre-soaking is also a very important part when you're rectifying your structures. If you are dealing with a structure that is 20 years, 30 years, 40 years old, the concrete is very thirsty. You need to have your concrete fully saturated surface dry. Means there should not be any free water, but the concrete should be saturated with water, obviously, you know, for 3 to 4 hours minimum. And then you have to cure it. This is a snapshot that I've taken for a precast girder, a girder in a precast factory, and they have some defects, and they're using a product in different layers. And there you can see they are applying first layer, then crisscross, then primer, then second layer. Now this is an old picture of our product. Now there are products in the market, and we do have as well, that are very extra high build. Their buildability, you can apply it one time. So that means you improve the site productivity, and the chances of multiple layers and any failure are also reduced. So that's why technological advancements are there in the repair and rectification industry as well. And you can see this is not a normal repair motor that is being designed and being repaired, the use for your girder. Definitely it must be a very special one that meets all the transport for New South Wales requirements. I think it won't be good to talk about geopolymer repair motors these days. This is a chemical bund in Sydney, close to my office, in fact, and they have used Renrock G, a geopolymer repair motor. Geopolymer is something new. Geopolymer means that you know, it has theoretically minimal cement and no cement maybe. So interesting for engineers who are working into chemical industries. It's not only coatings, but you can repair it with this is how it looks like, a geopolymer. Very easy to apply and very resistant to sulfuric acid, hydrochloric acid, and all those acids. This is the finish. So there are materials. This is a picture from Australia for bridge repairs. So there are special bridge repair materials that could be used to rectify your bridge deck surface. Obviously, these has to be very special. I can discuss the details on an individual basis to let you know about how this is done and possible to do it for bridge decks. Sprayed on materials. This is a project from a UK project, but this is how for larger repairs you could also spray apply. This is a project in Victoria where there are spraying and repairing it with spray applied chemically. So you can see, I mean, the technology has gone much ahead. This is how thick can be used. This was a trial for a sprayed on material. And then you have a foam and pour product. Foam and pour, if you have any type of structural element, columns and beams or slabs that needs a very high void repair, there are high build foam and pour repair motors. And I have written some articles on foam and pour. If you Google it, you will find it definitely. Here you go, you have it. So concrete rectification using micro concrete foam and pour. As I said, this is a similar type of technology that is being used for your Burj Khalifa. Original concrete. That means these are available in pre-bagged as well. And you can see it can be applied up to 500 millimeter. Obviously, it depends on the orientation and the total volume. And there are some critical things that are required to be considered, and we get involved into it. For example, thickness to length ratio and all that, etc., etc. This is how it works for large gaps. It really reinstates the structure properly. There are also repair materials that are used to enhance the cover. So engineers, sometimes they face problems that, hey, you know, we are 20 millimeter low in cover because of some problem, the formwork slip and all that. There are products these days that could make up for the low concrete cover. However, it's very tricky. No one is going to give you in writing that we take the liability and responsibility. If it's a throughout complete project, low cover, it's a massive problem. It's a disaster. So it has to be rectified by belt and brace method. But if it's a section where you have small areas where you ended up with low concrete cover, there are products that are available to make up for a low concrete cover. This is a project, a car park in Sydney, where an old car park, they have used 5 millimeter thick overhead. And first they use 20 millimeter, 30 millimeter, then the 5 millimeter on the top for low concrete cover. Cracks. We will have another session for crack repairs. It's a big topic. But just to let you know, there are a few pictures from Australia. If you have bridge decks, soffits, cracks, this is how it's used with surface packers. You apply surface packers. These are structural cracks, non-moving. Has to be static cracks. And you just fill it with a low viscosity. Low viscosity epoxy is just like water. It's such a low viscosity that means the moment you apply pressure with a gun, it will find its way inside and it will travel within the crack and concrete matrix and fill all the gaps. And it will reinstate the structure to its original strength. This is how it was ended up after grinding it off, finishing the injection and applying anti-chloride, anti-carbonation coatings. This is another picture, another project in Australia, in Queensland. You can see here cracks. And do you know, looking at this picture, how deep are the cracks? Anyone? No, we don't know. So sometimes they do this type of structural assessment. This is a part of diagnostic analysis. You remember assessment process number 2. So when you have these type of assessments, it helps, but you don't have to do it every time. For injection, we have complete methodologies of how to do injection and how deep you have to go, what type of depth of packers should be used if you are using mechanical packers. But for epoxies, normally you use surface packers. And I'll go through that in maybe next session sometime, only about injection. For polyurethane injections, when you have water leakages, you use mechanical packers. You drill holes at 45 degrees and inject it. For epoxy, because they are low viscosity, like water, you can end up using your surface packers. So we are in the last few slides. It won't be fair if I don't talk about it, but I'm not sure if you have corrosion grooves here or not. But while I was in Toronto last year, there was a launch of a product which has a combination of galvanic and impressed current cathodic protection in one unit. So it's very interesting. This is a big project here in Australia that they're being used. And again, it's a different topic, but I just thought to add a few slides at the end. Maybe in this group, there are someone who is involved into corrosion activities. So just to let you know that we are heavily involved into galvanic anodes, impressed current cathodic protection for bridge piers and for ports and other important structures. And finally, the step number 6 for a repair philosophy is acceptance, that you do the testing, snagging, documentation, everything is done. So this is for large repair products, I'm saying. It's not like if you have a small defect in your construction bridge and all that, and you have to do all these steps and diagnostic analysis and all that, then you can just simply do a visual inspection as well, and it's a pretty simple process. And that's all from my side. Thank you very much for your patience. I have exceeded 5 minutes, I think, of my time, Jilani bhai. And if you have any questions, I'm open to that.
Thank you very much, Hamid bhai. Mashallah, excellent presentation. Very professional. मेरा हाल अब हम question answer start करते हैं. Just feel free if anybody has any question. कुछ question